Hi, thanks for watching our presentation. The topic of our paper is learning transferable representations for image anomaly localization using dense pretraining. Image anomaly localization has been applied in many different fields to assist practitioners to localize regional anomalies in images. The major challenge of this task is that it is often infeasible to build a comprehensive anomaly set because localized visual anomalies are often tiny and subtle, and they can take on different forms, and the concept of anomaly are often context-dependent. And given these challenges, earlier works usually treated as an unsupervised task. In recent years, there has been a new trend of applying self-supervised learning for the IL task. The reasons are that self-supervised learning is suitable for tasks with no access to a large quantity of label training data, and also learns more discriminative features than unsupervised models. Based on the training pipeline, one can categorize self-supervised learning into end-to-end or two-stage. In the end-to-end model, the same classifier is used in both training and evaluation stage. And the merit of this design is that because the classifier is trained on the target dataset, so it can often achieve excellent localization performance on the target dataset. But at the same time, because the parameters of the classifier is very biased towards the target dataset, so it usually shows very poor transferability to new datasets when given no fine-tuning or retraining. In contrast, in the two-stage model, the classifier used in the pre-training stage will be discarded after this process is finished. And in the evaluation stage, a new classifier will be coupled with the model to help do the prediction task. And this kind of design usually achieves good localization performance on the target dataset, and because the new classifier is not biased towards any datasets, so it can also achieve good transferability to new datasets. For the two-stage self-supervised learning models, one can further divide them into instance-level pretraining and dense-level pretraining. The major difference is that in the instance-level pretraining, the feature map is first put into a single feature vector before it is used for the loss calculation, while in the dense-level pretraining, the loss is conducted in the individual feature vectors within the feature map. And instance-level pretraining is more compatible with instance-level downstream tasks, which requires image-level prediction score, while dense-level pretraining is more compatible with dense-level downstream tasks, which require pixel-level prediction scores. And our hypothesis here is that since image anomaly localization is naturally a dense prediction problem because it requires pixel-level prediction, we think dense-level pretraining might be more compatible with IL task. Given these motivations, we formulate the image anomaly localization task as a two-stage dense training problem such that compared to instance-level self-supervised learning, our model can learn better representations for the IL task. And compared to the end-to-end self-supervised learning models, our model can show stronger transferability to new datasets when given no fine-tuning or retraining. Our proposed model is adapted from a dense pretraining model called PixPro. In PixPro, it crops two views from the same input image, where one view is sent to the main branch and the other one is sent to the momentum branch. The PixPro model adopts only positive pair for model training. In order for the two feature vectors to be formed as a positive pair, they need to satisfy the distance threshold, where their geometric distance in the original image domain should be smaller than a predefined threshold delta. The first issue that we noticed is that PixPro was originally proposed to learn representations for tasks such as semantic segmentation, and those tasks are quite different from our image anomaly localization task. For example, in this semantic segmentation example, both point A and B belong to the same category, which is a building, and this qualifies them to be a positive pair because semantic segmentation does not need to understand nuance within the building. But for our image anomaly localization example, although the point A and B both belong to the same screw, they represent different parts of the screw, where point A represents the screw thread and point B represents the screw head. Now, in order to accurately localize the anomaly in the image, which is a tiny chip in the screw head, the model better learns discriminative features between the screw head and screw thread. Therefore, point A and B should not be considered as a positive pair. And in our model, we adopt highly selective positive pair by limiting the geometric distance threshold to only 0.1. And here is a visualization of using the highly selective positive pair method in the input image. One limitation after applying highly selective positive pair is that it filters out some potential positive pairs that are not geometrically close enough. For example, the two yellow boxes in image X contain similar parts of the circuit board with a vertical groove in the middle, but because they are distant from each other, they don't qualify for the highly selective positive pair threshold. Therefore, we want to add them as a positive pair to the loss calculation, and we hypothesize that similar patterns should have similar features at the output layer of the backbone. So we aim to find the top one similar pair, Pi and Pj, from the output of the backbone, and we record their location in the feature map and add this pair into the loss calculation. Finally, as image anomalies can appear in different sizes, we want to learn multi-scale representations for anomalies of different sizes. And we use the convolutional block 4 and 5 of the backbone and couple each of them with a separate projector. And in this way, we extend the loss function to include two feature scales, denoted as C4 and C5. And our model follows the two-stage pipeline. In the pretraining stage, we pretrain the DS2 model using the aforementioned methods. And in the evaluation stage, we only include the DS2 up to the backbone part and replace the rest of the model with a Gaussian density estimator, which functions as a classifier for anomaly prediction. We first compare the performance of DS2 with instance-level two-stage models, and the results shows that DS2 outperforms all the instance-level baselines except category-wise cut-paste. We need to note that category-wise cut-paste trains a separate model for each category, while our DS2 trains one model for all the categories. So for a fair comparison, we train the cut-paste in the same 1-for-all setting as our DS2, and we find that when trained in the same setting, DS2 outperforms the cut-paste in the overall performance and also achieves more balanced outcome among all the categories. And DS2 also takes less time to train compared to the cut-paste. Then we compare DS2 with end-to-end models for their transferability. We train them on the METech 80 dataset and evaluate them on 3 new datasets without any fine-tuning. The result shows that DS2 shows better transferability than end-to-end models. And even if we adapt them into the two-stage models, DS2 still shows the best overall performance among all 3 new datasets. We also show some qualitative results and the ablation studies of our model, the details of which can be referred to in our paper. To summarize, we present DS2, a two-stage dense representation learning model for the IL task. Compared to instance-level pretraining, DS2 can learn better representations for the IL task with much faster conversion speed. And compared to end-to-end models, DS2 has stronger transferability towards new datasets without fine-tuning. Additionally, DS2 provides other benefits such as steadier performance and high robustness towards small training sets and small batch sizes, which can be referred to in our ablation study in the original paper. And thank you for watching our presentation.